We are talking about within subjects designs in this unit. Those are designs in which some of the observations are correlated with other observations. I've begun by reviewing what you should have learned in an earlier statistics course, and that is the pre-post design. That is actually the first design you probably ever saw that was a within subjects design. Why within subjects? Because you're looking at scores from a pretest from the same individuals in which you collect observations on a post-test. So those observations are naturally going to be correlated because they come from the same set of individuals. As a continuation of that review, I thought I would review how to do this in an R notebook. And so here I'm showing you an R notebook. I'm going to use an example of working memory training that comes from an actual study conducted with students with disabilities when working mathematics problems. That is, they revealed deficiencies and they were classified in a category in which they needed extra services. And one of the extra services that was provided by this particular research study was working memory training. The pre and post test here are actually two administrations of the same standard battery of test. That is, they're looking at parallel forms on a mathematics portion of a standardized test. So the scales are the same, the difficulty, the items are the same, the content is the same, although the questions are going to be a bit different from one form of the test to the other. If they did not have different questions, the students might remember the questions from the previous time they took the test. So this is a pretty standard way of looking to see if any gains are made as a result of an intervention to use two forms of the same instrument. So let me go ahead and load in the working memory training mathematics data, and let's take a look at it. I have it here. And we see we have two columns, pre and post. And everything we've done up to this point, the scores have been independent of one another. But here, within a row, those scores are correlated. Now, there is still independence here. That is, the rows are independent from one another. Person 1 should not be correlated with person 2, should not be correlated with person 3, and so forth. So we're still looking for independence of the individuals used in the study, as well as independence in terms of their measurement processes. That is, they're not allowed to take the test helping one another. They're independent in making these observations. And so in this particular file, I have 63 observations. Now, in the original study, there were actually 4 different treatment groups, but that goes beyond what we're doing right now. That is still a within subjects design and one that we will still look at later on, but that goes beyond what we're doing at this point. What we're doing at this point is only wanting to work with one group of individuals. So I took just one of the conditions. So here is one condition in which there was an intervention that occurred between this pre and this post. So note the variable here is time, before and after, but in between was the intervention. And so by looking at time or the testing results on 2 times of taking the test, we can measure the effectiveness of the intervention. And so that's what we're going to do right now. So looking at this here, I'm first of all going to make box plots, and notice that I'm making box plots of pre and post. So when I make those box plots of pre and post, you're looking here at the same individuals here in the pre box plot as in the post box plot. Now what you can't do here is link any particular scores in this box with any particular scores here in the post box. We don't know how the scores changed by looking at these, except as the group. As a group, it definitely looks like there was an improvement. As a group, there was improvement because we see that the interquartile range of the post is completely above the interquartile range of the pre. There's a little bit of overlap of the upper quartile of the pre with the post, with the interquartile range of the post, but no overlap of the upper quartile of the post with the pre, which is pretty important given that these are the same individuals. So did the intervention help? It sure looked like it. But now let's go ahead and look at a different way of studying this graphically. I'm going to create a new variable from the existing variables. I'm going to create difference scores, and I'm going to go ahead and add it to the data set. So here are difference scores. Let's go ahead and look at that. So again, the difference score here is from the pre and post on row 1 from person 1. So notice that that score now tells me that they increased by 16 points. As I scroll through the data, I notice that I only see one negative sign here, and that's for person 12. Person 12 went down 4 points. If the intervention had not been effective, you would have expected that the individuals would have gone down in about the same rate as what they went up. That is, you would expect it to almost be by chance of whether they're going up or down if the intervention was not effective. But here I notice that they're almost all except for one of those 63 individuals, unless I missed something, and I don't think I did, all except for one actually improved. Let's see if there are any zeros in here. Looking. No. Oh, here's one. So there's one person, there's two people that did not improve. One went down and one stayed the same. Everyone else went up. So when I go back and look at this box plot, it's a single box plot, but notice it's based on a baseline of 0. So moving across here, thinking of 0, of a horizontal line coming across there, that would indicate no change. And I noticed almost all, not quite, but almost all of that box plot is above 0. I also get to see the magnitude of the changes. The interquartile range here looks to be like from just above 10 to close to 30. So between about 10 and 30 for the middle 50% of the individuals, that's how much they gained on the exact same math test after receiving working memory training. Getting some summary statistics, I'm going to go ahead and do it all in one fell swoop, get pre, get post, and also get difference scores. So when we look at the pre, this is the baseline. This is what it looked like before there was any intervention. When we look at post, we see that the post led to or was a result of an intervention, or actually the change from pre to post is the result, but this is what happened at the end of the intervention. I noticed that there's more variation on the post than there is on the pre, which means that there was a differential effect. If the effect had been the same for everyone, then we would expect to have seen about the same increase for everyone, and therefore, or it might have been about same increase for everyone if the effect was the same, and the standard deviation would have been about the same. Looking at the difference scores, which actually shows me the combination of pre-post, how much change there was, I see there was an average change of about 21 points from pre to post, an average difference score, an average gain. We sometimes call these difference scores gain scores when we take post minus pre. So the average gain score or average difference score is 21. But those difference scores ranged from going down 4 all the way up to going up 63 points. Notice though, even the first quartile at the low end went up 12 points. If I want to do inference on this, there are two formats for constructing confidence intervals for making inferences. Both of these are one sample procedures because the confidence interval is for the population mean of the differences. So here is one method. We're taking the t-test and we're taking post and pre and putting both of those variables in as arguments. But when we do that, we have to indicate that these are correlated. That is, paired equals true. So we know that we're pairing every post-test score with every pre-test score. And when we run this, we get here the mean difference of 20.94 that we found right back up here in our summary table. But here we get a confidence interval for that difference. So again, this is a one sample procedure because this is actually a confidence interval not for pre, not for post, but for the difference scores created when we take post minus pre. And this little command here does that automatically. So this is the difference right here between post minus pre, telling us that we believe that the average difference outside of this study that can be inferred is somewhere between about 18 and 24 points. That's the average increase. Pretty substantial increase, an average increase between 18 and 24 points, especially since I believe the battery of tests allowed for scores. Well, I don't know for sure, but I think it's 100 or 200. But in any case, as long as it's not much more than that, 18 to 24 would be considered substantial. The second method gives you the same result as the first, and that is we just go directly to those difference scores that we created way back up here when I created the difference scores. Now, if you didn't make the difference scores by hand, this is the method you would use right here. But since I did make them by hand, I can run the t-test on the one sample of difference scores. This makes it very obvious that this is a one sample test. This one here, it would be easy to be confused and think that it's a two sample test, except that the post minus pre is what's being done when we pair them. Notice the results are identical. Here's the confidence interval when we did one sample t-test were difference scores. Here's the confidence interval up here when we did a pair test t-test. We could also look at the outcome of pre-post test designs as a categorical variable. So that's one of the things that I showed you or stated in my presentation. We're actually not going to spend much time with that in this course. I teach this in a separate course, but in this course, I'm just going to briefly review for you from perhaps your first statistics course where you looked at how much people changed as whether they did, rather how, instead of how much they changed, whether they did change. So here I'm creating, you don't need to know this particular R code. All I'm doing is creating a new variable in my data set that I'll show you, indicating whether or not folk improved. And so here you see that -4 here has a no next to it. And there's one more no, I think. Yes, here it is. And that's the 0 difference. So those two cases, one person went down a little, one person stayed the same. Those two cases did not improve. So if I look at the frequencies of that, here it is. If I look at the proportions for that, here they are. And we see that about 97% improved. If I use prop test, then I can actually get from that I would be able to infer outside of this study that if we were to conduct this in replications, we see something other than chance taking place for this increase, because we would project between 88% and 99% improved, which is substantial. This doesn't show how much each one improved. That up here is where we get that. On average, that it would be between 17 or 18 and 24 points. But notice that both of them provide different information, and those two pieces of information provide the kinds of outcomes. One of them provides the kind of outcomes you might be interested in one situation and the other one in another situation. So when I say to you that on average there was an improvement of well, let's take the descriptive statistic right here, 21 points. When I said on average the improvement was 21 points, that may be of most interest to you, but I bet it might also be the case that you're not wanting to know that the average was 21 points, but you're wanting to know how many students did this actually help. And you could get an average gain of 21 points with a few of the students gaining a lot and some students gaining very little or not at all. Whereas what we're seeing down here, when we're looking at this 97% of the students improve, that's not showing us on average what improves. So it's not dealing with a quantity, but it's still providing useful information of how many students were actually helped by this treatment. And here we see it's 97%. So both cases are within subject's design. Both cases require that we take into account the correlation. Here we're looking at a single proportion. That is that 97%, and the confidence interval is about a single proportion, not two proportions, because these are correlated results. And here we're looking at a single mean and a confidence interval for a single mean. So this is a review of how we analyze data from a pre-post design. But in this particular course, because it's a second statistics course, we want to go further than pre-post designs, and we want to talk about other ways in which correlated data can be beneficial besides pre-post designs. So we'll continue looking at some of those possibilities in the next video.